Hello, today we are going to talk about cross product between two vectors. In my previous video I described dot product between two vectors, and I have to say cross product is just slightly more complicated than dot product. There are two reasons for that. Reason number one is that cross product will give us result that is vector, as we will see today, whereas dot product gave us result that is a scalar, and in principle it's always a little bit easier to work with scalars than vectors because vectors require three pieces of information to properly describe them: magnitude, orientation, and sense, whereas scalars only require one information, that's magnitude. The second reason dot product was a little bit simpler is because dot product was related to cosine of the angle between two vectors for which we are calculating dot product, and we will see today that cross product is related to the sine of that angle, and sine ends up being more sine sensitive, and therefore we have to pay attention on the order of the product, or otherwise we can end up with a mistake. It will be clear when I start explaining it here on the paper. Let's do it. I have two vectors, A and B. Cross product A cross B is defined as intensity of A, intensity of B, times the sine of angle theta, where theta is angle measured from A to B, and it is always the smaller of the two angles, because I could go in this direction and measure angle, but we always choose the smaller angle. However, this is not the end of the story. This is magnitude of cross product, but cross product gives a result that is vector, so I need to add here a vector that will transform the right side into vector. And I do that by adding a unit vector which I will call n over here. Now, what is the direction of this unit vector n? The direction follows the right-hand rule that I described in my video on Cartesian coordinates. And that rule says the following: turn A into B, and as you are doing it, an imaginary screwdriver would advance down in this case, because this is clockwise direction. As you are turning A into B, a screwdriver would advance down. For example, if you are turning B into A, it is counterclockwise direction, a screwdriver would emerge from the page. Let's say I have these two vectors, A and B. What is cross product? And namely, what is the orientation of cross product? Look, right hand rule. You remember in my video on Cartesian coordinates, thumb is the z-axis. So if I want to make a cross product between these two, the way I do it is A cross B, so we need to rotate A into B. I wrap my hands in such a way that my tip of my fingers is rotating A into B, and in this case thumb is going up into the screen, into the camera, and that would be the direction of the unit vector when I cross A into B. Now, if I cross B into A, when I wrap my hand in a right hand, always right hand, to go from B to A, look, my thumb is going in the opposite direction, and therefore you can see that A cross B is in up, and B cross A is in the opposite direction. Magnitude is the same, but the direction of these unit vectors are opposite, and therefore B cross A is minus A cross B. A cross B is minus B cross A. And this is something that was not the case when we had dot product. Remember that dot product A dot B would be intensity of A, intensity of B, cosine of angle theta. But we know that cosine of, for example, minus theta is equal cosine theta. So it really doesn't matter in the case of dot product if I go from A to B like indicated here, or I measure angle from B to A, because we are saved by the property of cosine. However, in the case of sine of minus theta is equal minus sine of theta, and therefore we get that A cross B is minus B cross A. When we have A cross B, sine theta is measured from A to B. Remember that. You measure always from the first to the second. Similar what I did in the case of dot product, I would like to relate this to right-handed Cartesian coordinate system, where this is x, y, and z. Positive like so. And we have three unit vectors, I, j, k. Thanks to these properties of cross product, we have that I cross I is equal to j cross j equal to k cross k equal to 0, because sine of 0 is 0. However, we also see that I dot j is k, and this is something to remember, because this is the official definition of right-handed coordinate system. In my video on Cartesian coordinates, I described what right-handed coordinate system means, but without invoking this relationship, because back then I assumed we do not know cross product. So I explained it in a different way. But now when we know cross product, this is the official definition of right-handed coordinate system. We can also see that j cross k is I, and k cross I is j. Remember, following this rule, we cannot just reverse these. If we reverse these, we get negative I, for example, in case of this cross product here. You might say, what is the motivation to invent cross product? And there are a few of them. First is torques, and I have entire playlist on torques. We know if we have a pivot point P over here, and we have some object, let's say here, and we apply force on this object, like so, force F. This is radius vector between the pivot point and where the force is applied. We know that torque is defined as the cross product between R and F. R cross F from this definition will be intensity of R times intensity of F times the sine of the angle between R and F. So what I do is I translate F over here. Now remember, I measure from R to F, and I measure this smaller angle, not this bigger angle. So this would be intensity of R, intensity of F, times the sine of this angle theta. Another motivation to invent cross product, let's say 2, is area of parallelogram. I have vector B and I have vector A. I construct a parallelogram out of these two vectors. A cross B is the area of this parallelogram that I will call S. Why is that the case? Well, let's drop a normal from the head of this vector B to vector A and call this normal H. This is angle theta. What is the direction? Well, this, because I'm crossing A cross B, so I'm measuring from A to B. What would be the area of this entire parallelogram? Let's call it S. Well, we know that from elementary school, that would be length of this side A times H. That is further equal A. What is H? From our video on trigonometry, you can immediately see that H is B sine theta. And look, this is exactly the magnitude of A cross B. But in order to end up with area that is vector, I need again to add normal. And the normal is in what direction now? Help me with this. A cross B. I am crossing A into B. A screwdriver, that is counterclockwise direction. A screwdriver would come out of the page. So this area would have normal vector like this, that is coming out of the page in this case, and that is represented with this unit vector n. Again, you see great importance of unit vectors in vector calculus. The next question is, how do we compute cross product? A cross B. Well, we can again use the rule of components that we had in the case of dot product as well as adding vectors. So that would be AXI plus AYJ plus AZK, where these are components of A, cross BXI plus BYJ plus BZK. Now I take cross product between these two, but notice that I cross I will be 0. So this one doesn't exist. Then I take this one, I cross J will be, for example, AXBY, and I cross J will have K component. Then you take this one with the last term here, it would be AXBZ. I cross K, that should be minus J. So that would be minus J. And now you can continue on your own and see how you can compute cross product component by component. But to be honest, not many people are using this method because you need to pay attention to these signs, as I was thinking here for some time. What we do instead, we use the rule of determinants. So we say A cross B is equal, and then we use determinant. First row is unit vectors I, J, K. Second row, component of A, AX, AY, AZ. Third row, components of B vector. And now we know how to calculate this determinant. First, along I cross this column, this row, and I get AY BZ minus AZ BY, then minus J. I cross this row and this column, and I get AX BZ minus AZ BX, and plus K component, cross row, cross column, AX BY minus AY BZ. Let's just compare with this here. For example, AXBY. AXBY is here. Positive K. Good. AXBZ is here. with negative j, all is good. Now I would like to mention something here, as famously Professor Herb Gross, one of my heroes when it comes to teaching mathematics from MIT, he said, if there is a list of reasons for inventing determinants in mathematics, calculating cross product would be at the very bottom of that list. Determinants were not invented for cross product, but it turns out they are very useful in this calculation, and we use them all the time. And I hope you remember I use this in my video on centrifugal force as well as Coriolis force and so on. Lastly, few notes on cross product. A cross B plus C is equal A cross B plus A cross C. We also have something called vector triple product that I used in some of my previous videos. A cross B cross C. And please remember that in the case of dot product, we cannot have this triple dot product, and I explain why in that video. But in the case of this, remember the rule ABC. When you cross these, you have back minus cab. So B A dot C minus cab C A dot B. This can be proven, but I am not going to do it here for the sake of shortness. Lastly, we also have something called mixed product, and that is A dot B cross C. And to calculate this, because remember, the result has to be what? Well, it has to be scalar, because this will be vector, and then I carry out dot product with this vector, so result has to be scalar. And the way to calculate it is again using determinants. First row is AX AY AZ, components of A vector. Second row BX BY BZ, components of B vector. And CX CY CZ are in the third row. And now I'm not going to calculate this determinant because it's the same principle as here, of course. That can be your homework. This is called mixed product or scalar triple product sometimes. Let's think about it a little bit. What does this represent geometrically? You will see, if you think about this a little bit, that the mixed product is the volume of a parallelogram defined by ABC. So we have, for example, here vector B, here is vector C. What is B cross C? That will be this area. We just discussed that a few minutes ago. And then I multiply that with vector A, let's say like this, vector A. I multiply using dot product. I will get the volume of this kind of cube out of it. Sorry for this mess over here, but what I'm trying to demonstrate without using new slice of paper and contributing to climate change, I'm trying to demonstrate that A dot B cross C would be volume of parallelogram defined by A, B, and C. Also notice that something that I realized when preparing this video. People write this A dot brackets B cross C, but really we don't need brackets. Why don't we need brackets? We don't need brackets because we cannot first evaluate A dot B. If we evaluate A dot B, we will get scalar and then we cannot cross it with C. So these brackets are really useless, because we must first evaluate this to get vector, and then dot product with A will give us a nice result that is scalar at the end. So result is scalar. cross product between two generic vectors in all of its glory. Until next video, goodbye.